And once again, so this will be a sand body, and the channel itself will eventually fill up with mud. So in that way, you isolate the sand bodies, the sands that form the beach and sand dunes, and but that sand that is eroded away will accumulate either behind or in front of the what are called washover sands here, the barrier island sand bodies. So then, what do we have here? Let's take this bottom diagram or picture. We have our shoreline, and then we have a little delta forming back in here. That nice light colored sand. And so this is an example of a flood tidal delta, okay, where the sand is being pushed in the landward direction. And this tidal channel will eventually fill up with mud and form a vertical wall or a vertical barrier that compartmentalizes this sand body down here. Here's another example. You've got a barrier island sand body here, and you've got another one there. And then you see back up in here, you've got a tidal channel. And the flood incoming tides are stronger than the outgoing tides. And so eventually you build up a nice flood tidal delta back here. And that can be a potential reservoir. Here's an example of an ebb tidal delta down here. And you can see the sand body there. You can see a sand body here. And here's your tidal channel right there. And then here's the outline of an ebb tidal delta. In other words, the outgoing tides are stronger than the incoming tides. Therefore, the sand is pushed, once it's eroded out from this tidal channel, it's pushed out into the towards the marine and open marine environment. So those are examples, and these little tidal deltas, they're relatively small usually, but they are quite good sand, and they can form reservoirs. There's some good ones up in I think Wyoming or Montana in the U.S. that are excellent reservoirs, for example, that are these types of deltas, tidal delta, either a flood tidal delta or an ebb tidal delta. Well, this is just a picture I put in for geologists. Again, the geologist looks at core, or in this case, the case with the beach, you can dig a trench right down there, and you see very diagnostic features. In this case, you've got the light color is sand, and the black color is shale. And so you've got alternating sand and shale here. And notice that the amount of shale is decreasing upward in this picture here, and the amount of sand is increasing upward. And that tells you something about the environment of deposition. What it's telling you is that with geological time, what is happening is that you're depositing more and more sand. Well, how do you get a situation like that? over a period of geological time where you're progressively getting more sand deposited and less mud. Well, that's an indicator of a possible indicator of a change in sea level, where you're going from a lower energy environment where you deposit more mud, down here and progressively more sand as you move up, meaning you're getting an increase in energy level of this zone right in here, your shoreline zone, and that can be attributed, say, to a slight drop in sea level, okay, where you're with a slight drop in sea level, you're getting more and more sand because you're getting a higher energy environment. And so it's clues like that that geologists use to get an idea of how sea level is changing and so on. And at a very small scale, you've got two different types of reservoirs, basically. You've got a very sandy one here, and you've got a more shaly one down there. And so your best reservoir quality in this situation would be up here, the uppermost sand. So if you knew you had a sequence like that, you would maybe want to drill your well and do your perforations up in the upper part of the sand rather than in the lower part of the sand, because you've got more shale associated with the sand down below. So subtle things, but they can be very important for well placement, for example. Well, I have to say a couple words about fossils. I'm not going to talk too much about fossils. Fossils are the remains of organisms, but what I will say is that there's two general types of fossils. One type, we call them body fossils, and the reason we call them that is because you can actually see the hard shell, the body of the fossil, after it's dead and buried in the sediment. So here you have a nice sandstone, shallow marine sandstone here, and embedded in that sandstone, these are oyster shells. These are old oyster shells, about 60 million years old, when those oysters were living. And oysters live in a very specific environment. They like kind of shallow water, not too much wave action, things like that. So that when you see fossils like this, oyster shells, for example, it tells you something about the depositional environment. It tells you were in shallow water around the shoreline, the marine shoreline, and that's what it tells you, basically. And so you get information. Now, not only can you get that sort of information about the environment of deposition of the fossil, but some fossils we have been able to accurately age date the time in which the fossils were living. So that's another thing why fossils are useful. Now, those of you working in fluvial systems, you don't find marine fossils. If you find marine fossils in what you think is a fluvial system, it's not a fluvial system. Okay, so you want to keep watch for these types of body fossils. Now, that's one type of one group. The other is what we call trace fossils. And they're called trace fossils because they you don't find any of the hard body parts, but you find some evidence that an organism was living in that environment of deposition. And in this case, see, those of you who went to Colorado School of Mines, you probably, the engineers ever take you to this outcrop up just south of campus?
No. Oh, yeah.
That's a classic outcrop, right? I forget the name of the ridge, but very classic outcrop. Everybody goes and sees. So many people go, and what they're looking at is these are dinosaur tracks. So you've got all these little dinosaur tracks here moving that indicated dinosaurs lived there at one time. There's no body parts, there's no bones or anything like that today, but you have these tracks, and so we call those trace fossils. And they're very valuable as well to tell you something about the depositional environment. For example, here, when you see these dinosaur tracks, you know that this sediment that contains the tracks wasn't deposited in really deep water, okay, because dinosaurs don't have those long legs. So it must be a shallow marine or even a non-marine environment that these dinosaurs were moving around in. So, two general types of fossils, body fossils and trace fossils. And I'm going to show you now an example of each and their importance. What we're going to do is start an exercise, and this is an exercise from Mexico that uses fossils and other criteria. I'm going to do the first part of this exercise for you, and then I'm going to leave the last part for you to do an interpretation of the type of deposits that we have and what kind of reservoirs they might be. So we're going to go to Mexico now, and the big field in Mexico is the Cantarell field. Now, the Cantarell field is a carbonate reservoir, not a sandstone, but it's a carbonate reservoir. And it was deposited somewhere 60, 80 million years ago, something like that. The carbonate was. Then it was tectonically folded and faulted, so that today what you have when you look at a cross-section, you see a fault block that's kind of bounded right here, and then another fault block on top that is thrust over the older fault block. And the Cantarell field occurs right in here, right in that axis of the fold. You've got top seal because you've got this overlying thrusted block forms a top seal to reservoirs. Your reservoir itself, the structure is an anticline, and so it's a conventional type of reservoir. It is gas. It's a gas field, and in this area. And how I became involved in this was that Pemex, that operates the Cantarell field, the Cantarell field started some years ago, started a very serious decline. And that was the main field in Mexico, and it was a big field, made a lot of money for Pemex and the Mexican government. And so when that field started to go on decline, the Pemex, the Mexican oil company, government oil company, got worried. And they said, well, we better do some geology. What went wrong? There's my old expression again, what went wrong? I get all these phone calls. Somebody says something's wrong. What can you do? So they usually say the geology is wrong. They fix it. So, at any rate, that was the case here. What the strategy that PMEX used was to try to, well, they used two strategies. One was to find some ways to improve, to bring up the production in Cantorell Field. That was one strategy. The second strategy was try to find more gas in other areas to bring up production, to replace what was being lost from Cantorell Field on the decline. Well, I became involved in this second option. PMEX said, can you find us some more gas reservoirs to bring up production? And so that's how I got involved in it, and actually 2 Columbian graduate students of mine did the work, and I just kind of supervised it. And I want to go through some of that with you now, how they solved the problem. In this case, the problem being, can you find some more gas fields? And the answer was yes, we could. And I want to take you through how we did that. So here's a regional seismic line with your regional structure. You have a big fault here that's called the K fault. Okay, it's called the K fault. And it's a, here you see the anticlinal structure here. Cantorell Field, this is where Cantorell Field is, on top of this structure, this anticline, and it's bounded by faults, okay, on both sides. So that's Cantorell Field. Now, the one thing that PMEX, they put one condition on finding new field, new gas fields, and that condition was they didn't want to drill any wells, okay? So in other words, there were a lot of wells that had been drilled already down to the Cantorell Field, and they said, well, just look at the logs and things that stratigraphically higher, and see if you can find any gas fields, additional gas fields within the stratigraphic column above the Cantorell Field. Well, they did drill one well, and it turned out to be a discovery well, and it was right here in this position, and some tertiary rocks, sandstones, were the reservoir. They occurred in this little teeny rollover anticline that I colored in yellow dashes here. So that was a discovery in tertiary rocks younger than Cantorell. So PMEX said, well, we've got a lot of wells that were drilled from the surface down to the Cantorell Field. So look at those wells so we don't have to drill any more wells, and just see what you can see. When the wells were being drilled down to the Cantorell Field, nothing was tested above the Cantorell. Well just went right down without any testing of the younger stratigraphic section. So that was our goal, and gave it to, like I say, the 2 graduate students, 1 male and 1 female, and that becomes an important part of the story as well, as I'll say later on. And so here's the type log from the discovery well. What they found were there were 2 intervals that had commercial gas, and we called those Reservoir 1 and Reservoir 2. Reservoir 1, right down here, is Reservoir 1, and Reservoir 2 was a sand body right up there. Now that fault, this fault here, right in there, that's this cave fault that occurs right in here. Okay, so it's kind of like a bounding fault in the younger strata on this upper fault block. Okay, so 2 reservoirs. And this is an interesting part of the story. One of the graduate students, the male, we got the data from PMEX, and I had to go out of town for a week. So I gave all these logs to my graduate student, the guy, and said, see what you can figure out while I'm gone next week. So he had black hair, and when I got back, his hair had turned gray. His hair has turned gray because he almost went crazy trying to do some correlations. Look at all the different sand bodies that you can see there. There's all kinds of sand bodies, and he's trying to correlate these. I said, no wonder you've got gray hair. It's impossible to correlate just by looking at log shapes. You need something else, marker horizons or something like that, if you're going to try to correlate different well logs. So we backtracked and started again, and we looked at these 2 intervals, reservoir interval 1 and reservoir interval 2. Well, here's kind of a close-up of that interval now, okay? And here's your, this is a gamma ray log. And what you can see quite clearly is that this upper reservoir 2 is right here, and it's a kind of like a finding upward log pattern, okay? Meaning your best sand is at the bottom, and it gets more shaly upward. So that was one of the characteristics of one of the reservoir 2. Reservoir 1, which occurs down here, is a little more difficult to see because you had that cave fault down nearby. But when you look at an enlargement of the log there's the cave fault. And what you see here is that this is kind of a blocky log pattern. When you looked at all the other log patterns in that well, what you mainly found was, if you can see by my arrows here, was a getting cleaner upward log pattern, cleaning upward pattern, cleaning upward pattern. Most of the sand bodies were ones that were from the bottom to the top of the individual sand. They were getting coarser grained upward, like you would get in a progradational sort of depositional system. In fact, about the only 2 sands that did not show that pattern were the 2 reservoir sands. So right there, first of all, just by looking at the log shapes, we got an idea that those 2 reservoir sands are somehow different, geologically different, and that's why they're productive and the other sands are not. So that was our first clue. The guy, some of his black hair started to come back, okay? Reverse aging, it's called. Okay, so that was the first thing we saw. So to show that again a little closer, here was the reservoir 1, resistivity in a gamma ray log. Reservoir 2 was right here. And you see kind of a blocky log pattern, blocky finding up pattern. All the other ones get cleaning upward. Here's one there. I'll use a different color to do that. Here's one there that's cleaning upward, another one there cleaning upward. Now, this one's a little bit blocky, but it wasn't a reservoir. But this one cleaning up, cleaning up, cleaning up. See, most of them have the opposite log shape to the two reservoirs. That was the important point, the first clue that as to why those only two sands were reservoir. I think they did test this zone right in here, but it had some gas, but not commercial gas. Okay, well, this is a picture like a geologist makes when they describe a core or something like that, or an outcrop or whatever. And this pattern here is you're getting sandier and cleaner from the bottom to the top. And what that was, that's these patterns here. Red ones. Now here, this log pattern is just the opposite, where you've got your thick sands at the base and it gets thinner and shalier upward. And that the geology that corresponds to that log pattern is where you had your two reservoirs, there and there. Okay? So that was the difference. Now they're kind of subtle differences, but they turned out to be real differences and gave us clues as to why only those two sands were reservoir. Different log patterns. Well, we could put this in terms of change in sea level over time. What's happening here, you start out at the bottom. Remember, geologists always look at things from the bottom to the top, the way they're deposited. So you had at this location, you had shale, then starting to get a little more sand and more sand and more sand. How you explain that geologically is just you have progradation of your sediment bodies. So that coarser grain sediment is always deposited on top of finer grain sediment. That's what this is showing you here, what we call a cleaning upward pattern. Here is just the opposite, where you have a marine transgression, not progradation, but transgression, and the sands are deposited on the shoreline. So these sands down here are shoreline, and with transgression at that one location, progressively as the water depth increases, you're going to get more and more shale. So you end up with what we call this finding upward pattern. So once again, progradational, or we can call that marine regression if we want. And this is transgressive, or a term I used on Monday, retrogradational. I like transgression better. It's easier to remember. And so this one has your best sand bodies at the base and getting shalier upward. This one has your best sand bodies at the top, getting sandier upward. And the corresponding log patterns, you'd get a gamma ray log that looks like this. And here you'd get a gamma ray log that looks like that, okay? Well, once again, it was this log pattern that represented the reservoirs. So let's carry on and see what else we found out about these reservoirs. Well, there was some core available, and these were body fossils. And you can see here's looking down at a piece of core and all these shells. These shells have to be very thick-walled clam shells that lived millions of years ago. And clams, we know that the higher the energy of the depositional environment in which the clams live, the thicker the wall is going to be of their shell, because it's a protective. The shell protects the inside body parts, just like our skeleton does. So that gave us a clue that we were dealing with a high energy environment, because these were very thick-walled clam shells. This is, let's see, yeah, this is probably a good place to take a break. So why don't we take our break, and we'll come back to this after the break.